In this video, we will look at an implementation of a particle system within our Android framework. It builds upon the theory-based lecture where we outlined, in principle, how particle systems can be created and mentioned that they're very broadly used. And we'll see a number of examples here of the types of effect that we can create using a particle setup. In terms of what we're looking at, so it's one of the demos that were sent out as opposed to part of the Gauge framework, so not integrated into Gauge. It's the type of thing that you may wish to do in terms of making use of this if it fits into the type of game that you're developing. So within our demo package, we had a particle folder within that, and there was a number of different classes within this, from a particle to a particle emitter to particle settings to particle system demo, demo fragment, a world, and a vector 2. Now, most of those are, well, they're all related to this particular demo. Most of them are concerned with the setup of the demo. But we'll go through all of them, but I'll really just focus on the ones that embed the particle system itself. And by way of illustrating what it is we're talking about here, if we were to run our demos, we get to list the ones that are available. Particle system demos down towards the bottom. So we can run this and it triggers the demo, and initially it's showing a explosion effect within the demo. And wherever I click, that'll determine then the center location of the explosion. And each time explosion happens, it's slightly different from the other explosions. But a classical, if you like, use of a particle setup. There are a few other ones we've implemented in this, so we can step through those. This one here is a smoke plume. So whenever I click, it's going to emit a number of particles that gives the appearance then of a rising column of smoke. May look a bit jittery on your screen. This is part of the issue of trying to capture the emulator within the particular video capturing software. So we're dropping quite a lot of frame rates or frames as we go through this. But that gives us the illustration of how we can simulate something that looks a bit like smoke. In terms of other options that we have, if I can iterate and step through it. Now, it can be a bit difficult getting onto it, just in terms of having the UI pick up the interface. There we go, that's the one I was after. So this tries to iterate it through them, but because it's based on a click event, we're missing a lot of the click events within the emulator because they're recording it. This is more obviously a particle effect, and as I move the mouse around, you can actually see how the particle trail follows the path of the mouse. If I just keep the mouse in the same location, then we're spewing out a whole bunch of particles. It's more obvious in this case that you can see each individual particle, each sort of purple circle that's created, and then gravity happens to be pulling it down, and it sort of fades out towards the bottom of the screen. So these are three different types of particle effect that we have available within our setup, and we want to go through and have a look at the underlying code base. It's exactly the same piece of code that generates all three of these. We're just configuring it ever so slightly differently. So in terms of things that we have that I'm not going to go through in great detail, you can have a look through the demo stuff yourself. Start off with the vector 2 class. So vector 2 is simply, well, as the name suggests, it is a two-dimensional vector, an x and a y coordinate. There are floats in this case, and we'll use this when we're specifying the position of the particles, the velocity of the particles, the acceleration of the particles, so we can have proper floating point numbers. Generally, constructors and other things within this are reasonably straightforward. A few useful methods for zero, getting the length of the vector or the length squared, and updating or adding other ones to it. So a very simple vector 2 class. The particle system demo and the particle system demo fragment are simply the demo ones. So this is the one that links this particular thing in. All of the demos that we have, well, there's only three different particle effects, are bundled up within our particle world class. And that's our very simple approximation of the world within which we are displaying our particle systems. The rest of the demo fragment, it basically just creates the particle world, sets up a touch listener, and down towards the bottom it has our simple time loop for updating and calling the world at regular intervals. So that's fairly straightforward things we've seen before. The last one I'm going to go reasonably quickly is our particle world. So this is notionally where our particle system lives within. And within this here, we'll introduce some of the the higher level concepts that we'll then look at more detail in terms of the coded implementation. So we have a particle settings file, and that's key for controlling the type of particle effect that we actually will generate. Then we have a few flags down here for trying to control going to the next one, and whatever bitmap we're using for the particle effect. For each of the different particle effects, whenever we were displaying them, they were in essence being displayed using a single image. And we'll come back to that in a second. So for each of them, when we're showing them for the fire one or for the particle effect, it was one individual image that we had being displayed. I'll probably find these ones in here. So this is our purple particle. There was our smoke image. You can see here is actually a transparent image. And here is our dull explosion image that we were using. This was going to be combined additively. So that represents the three different image types that we had displayed. Within this here, for setting up the world, we initially started off with our explosion particle effect. We created an emitter to use that particular setup. So an emitter, as mentioned in the theory lecture, is the thing that controls how particles are emitted. They are created, they're birthed, if you like. Depending on the settings that we pass in, we'll create them in different ways. The settings will also help determine how those particles are initialized, how they move, how they evolve. Bit down here in terms of the try, just loading in a few of the images that we want to do. If we're updating it, there was a simple bit to try to see if we sort of clicked on the button and if need be swapped to the next particle effect. Other than that, we're simply going to our emitter and we're asking our emitter to update itself. So it updates the particle effect. It creates more fire or smoke or whatever it's going to be depending on the effect we're simulating. If we do want to set up the next particle system, this just alternates between the smoke and the explosions and the ordinary particle effect, the purple one that was created. So we iterate between these different effects. For drawing it out, very straightforward. We clear the screen, we go to the particle effect and the emitter, and we ask it to draw itself out. So notionally, the emitter will look after all of the particles that it manages. So when we're drawing the emitter, what we actually will be drawing are all of the active particles that are alive, that are managed by that particular emitter. That's what gets to be drawn to the screen. And then finally drawn the button for going on to the next one. So that's all set up. So the three relevant classes within here that actually contain all of the things are a particle class, our particle emitter, and particle settings. We'll start off first of all looking at the particle. So these are the individual elements that go together to form our overall simulation. And it's reasonably straightforward. So, and again, this is an implementation. Depending on your implementation, you probably will have most of these. You may have additional properties and fields coming into it. So each particle has a position, an X and a Y location, has a velocity, how that particle is moving, and has an acceleration, how the velocity is changing. And we use all of those things. So depending on the effect that we're doing. So for example, if it's something like a smoke effect, there we want the particles to be created at the bottom of the screen and sort of to drift up to the top. So in that case, they'll be given a low upwards directional velocity. We probably wouldn't change the acceleration very much. If we're dealing with an explosion, then an explosion has a rapid, sudden expansion outwards, which then sort of decreases in speed the further it goes out. So in that sense, we want to give it a high initial velocity outwards, but to have the acceleration going in the opposite direction. So actually it acts to slow the thing down. So it expands out very quickly, but it slows down the further it gets out. So these are some of the things we would be controlling within the particle effect, and we'll do that through giving particles appropriate accelerations, velocities, and so on to update their position. We also have an orientation, so these images will be drawn rotated around, gives a bit of variability to them, and some effects you would actually want twirling or spinning images. And the angular velocity controls the speed at which we will twirl or spin those particles. Some particles, we wouldn't do that, just give them a random orientation. Other ones, we do want to have them spinning and moving as they move. For example, the smoke one, you want to have sort of the billowing clouds going up and going around. So we'll give them a small angular velocity to get that coming out in the simulation. The images that we draw, we can also scale them. So sometimes when we're creating them from the emitter, they're small, and as they go up, they enlarge and get bigger over time. That would be the case, for example, for the smoke effect. So the cloud of smoke sort of expands out, which is another way of saying when we're drawing our smoke image, we draw it bigger as it moves up towards the top of the screen. So the scale controls just how big we're going to draw that particle, and the scale growth controls how much we change that from one frame to the next. Are we shrinking it? Are we increasing it from one frame to the next? All particles that we create are born. They evolve and change for a certain period of time, and then they die at the end. So each particle has a lifespan, and lifespan will be a certain range, but it'll differ a little bit from one particle to the next. So we store that there, how long that particle is going to live for, and we have to then store when that particle notionally was birthed, or how long it has been alive for. And we'll use that then as our trigger to work out if it has expired and come to the end of its lifetime. So a reasonably straightforward set of properties. You could add in more fancy ones there depending on the effect that you are simulating. A few useful methods, one for are we alive? We've got initialization method here, where you pass in the position, velocity, acceleration. All the other ones, simply just store it. We have an update method. As you'll see here, for update, we're passing in the delta time, how much time has elapsed, and we're using that to update the velocity given the acceleration, to update the position given the velocity, update the orientation given the angular velocity, to scale it, and to update the time since birth. You'll notice within this that there's no draw method. And you'll notice, I hope, that we also said that a particle basically is just an image, a bitmap that we draw to the screen, but within the properties here, there's no bitmap. Now, that's not a necessary outcome, and you could create a particle system where each particle did have its own bitmap and was responsible for drawing itself. For this particular implementation, we're assuming that the emitter will hold the bitmap that particular simulation uses, and the emitter will be responsible for drawing each of the particles at the appropriate location. It doesn't have to be that way, that's just an implementation specific aspect of it, but there's no necessary or compelling reason why it ought to be that way there. So if you want to do your own version, sure, you could put a bitmap, a reference to bitmap within each of your particles. You could have each particle being responsible for drawing itself. It is swings and roundabouts. Sometimes if you have centralized management and control of them, it can be a bit quicker to iterate through and actually to draw them as need be, but swings and roundabouts. Particles, we'll do particle settings next, because this is the thing that controls each of the different effects that we have. So the one at the top is for our smoke effect, and you see it's just basically a bunch of numbers. Then we had one for our fireball effect. We had one for just the particles dropping down as the one moved around. So you can see that each configuration is defined by a bunch of numbers, that and nothing else. And some of the things we have within this here is the image that we're using. So if we're doing the explosion, we're using our explosion PNG file, so one I showed you earlier on. We're saying whether or not we use additive or normal alpha blending. For an explosion, as we mentioned in the theory lecture, we want to draw additively. We want to brighten up the region of the screen. The emission mode is continuous as a burst. In this case, it's a burst. We create a bunch of them at the first time. Min and max burst time. So this basically says every single second we're creating a new explosion, a new burst of ones. Acceleration mode. So there's a couple of ones here. So this is aligned, which basically means that whenever we create particles, we'll give them a random direction within some boundaries. And if we want to align their acceleration, then their acceleration is in that initial direction. If it is non-aligned, it means then that their initial velocity and the acceleration that they have can be in different directions or pointing in different ways. So for the acceleration mode, if it is aligned, then we give the min and the max, min and max acceleration magnitude in that particular one. If it is non-aligned, then we give the directions within which the particles are allowed to accelerate. Gravity, so in this case here is 0, so explosion isn't affected by gravity, whereas for example the dropping particles, if we look at gravity, we had 9.8 downwards. So in this case, gravity was pulling our particles down. Minimum number of particles, maximum number of particles that we will create. So for this effect, we have each explosion has between 50 and 60 particles that make it up. Min and max initial speed. So every single particle initially has between 400 and 500 units by way of its initial speed. Min and max angular velocity. So again, there we're saying how much spin we want to give on it. So reasonable wide range. Min and max orientation, 0 to 360, any old orientation, want to randomly do it. The bits that the particles will live between a half and up to 1 second. So basically from half a second out, the explosion will be starting to fade. Full second out will have completely faded out. We also have then our min and our max size for each of the particles. So initially we're creating them smaller, and at the end of lifespan we want them to scale up to their full size. And we have our scale growth, so this just controls. Okay, well, we'll resume recording. Not like a fire alarm test mid-video, but I can't be bothered recording this again, so just going to carry on. So what we can do within this here is by changing the values that we have within our particle settings, we can control or alter the type of effect that we produce. So for example, if we were to take our explosion effect, and let's say that in terms of doing this here, we want to give the particles a stronger negative acceleration. So we will increase the amount that they decelerate. So as a reminder, for a particle, initially they expand out suddenly or quickly, and then we drag them, we slow them in by giving them a negative acceleration. And we'll make the lifespan slightly longer in terms of doing this particular one here. Take up to 1 second. So we've given it a greater decelerating effect, and we've made the particles live for slightly longer in terms of their overall duration. And we can have a look then just to see what type of effect this brings around. Sometimes for particle effects, a lot of the time then sort of just tweaking the parameters to get to the type of effect that you want to do. And often this is the type of thing that does make the difference between it. But we'll see what this does. I've got something in my mind, but well, okay, yeah, there you go. So for this particular case, compared to the previous one, we seem to have more of a fireball, if you like, in the middle, and then it expands out. Now, reality, what's happening here is the particles have been shot out, they've been pulled back, so that initial velocity isn't really overcome. Well, it is overcome. So it's overcome, and then they go in the opposite direction, and we see them shooting off in the opposite direction as they're accelerated in the initial direction that their acceleration has provided them in. But by controlling these things, you can control the different types of effect that you bring around. So it is quite capable in terms of what it is you can elicit by way of the different types of effects and properties. Okay, so that's our settings file with the 3 different options that we have within this here for the ones that we're simulating. Now, all of the magic, if you like, happens within our particle emitter. And we've set this up under the assumption that it will manage a single particle effect. So a particle emitter could be an explosion effect, particle emitting, or a smoke plume particle emitter. Now, again, as referring back to the theory lecture, this is just an implementation-specific assumption. The particle system and emitter that you might do could be quite a generic system that could emit different types of effects. This particular implementation is a reasonably simple one where it ties this thing into it. So in terms of the particle emitter, what do we have within this? A lot of things we are creating random values for, in terms of randomly giving it a velocity within a defined range, an orientation within a defined range. So we'll be using a lot of random number selection. And because of that, I don't want to be having to create and to recreate a random number generator. So we create one at the start that we will then reuse throughout this entire class. So we can see that in all of the other methods then we will actually be making use, or not all of them, but a number of the other methods will be making use of a random pre-created random number generator. So a few useful utility methods. We've got one random between. If we give a min and a max value, it'll return a random number, a random float in this case, between the min and the max. We have another one here for pick a random direction. Now, reason I have this here is that it takes in a min and a max scalar value, so this corresponds to an angle. So I could say between minus 45 degrees and plus 45 degrees. And what we are outputting here is not a random orientation, because I could just use my random between if I wanted to do that. Instead, I'm outputting a vector 2, a directional vector that points me in whatever random angle I've chosen. So in creating, for example, the smoke particle system, if I assume, for sake of argument, that say 0 is straight up, I might want to create particles between plus 15 degrees and minus 15 degrees. And by calling this method, I'll do that, but I'll get a vector output pointing me in the XY direction that will give me that desired orientation. And that's what I want, because I want to have a vector which I'll then use to give things velocities and accelerations and so on. So in doing this, we pick a random angle, and we then simply turn that angle into the corresponding directional vector, just simply using the cosine and the sine of the angle to get the x and the y elements output. We've got the context to which this belongs. We'll use that for loading things in and so on. We've assumed for this emitter it manages a single particle system. So there we have one bitmap that this particle system is going to be using. So it's a simplifying assumption. You might have a more fancy one if you have multiple different effects. You might want to take the bitmap and actually link it into your, if you like, set of settings or collection of particles associated with a particular effect. We are storing a few other things with the texture. We've got the texture center, because any times we are rotating or drawing these particles, we want to draw them at the center of the bitmap. We've got our paint object, which we'll use for fading things in and out. We've got a time thing here for time to burst if we want to have this being repeated in regular intervals. This is what we'll use to count up to that. And finally, we have our last location. Now, the last location is quite relevant here. For the effect where we were showing the purple particles as the mouse moved around the screen, we want to then remember where the mouse was on the previous frame. So we're calling it with the mouse was over here, now it's over here. That gives us 2 points. And if we have to create particles, we can string the particles across that particular distance. So we're not creating our particles all in little bunches of space at the same space. We're looking at how the mouse has been moving in that particular demo and creating them uniformly over that distance. So our last location will give us then the ability to work out where we were, where we are, and then to string them over that particular distance. This is important stuff here. We have 2 linked lists, one of active particles and one of free particles. So active particles are any particles that are currently alive and taking part in the simulation. Free particles are particles that we have available but are not yet or currently being used. And we want to retain a store of free particles simply for reasons of performance. Because we create particles very frequently and then dispose of them, we don't want to be putting a burden on the garbage collector. So we will create a bunch of particles at the start and we'll reuse those particles. And whenever one comes to the end of the lifespan, we'll put it back into our queue of free particles and then reuse it for later requests. So it speeds things up quite considerably. We're using a linked list as opposed to, for example, an array list, because in this particular case, we generally are just iterating from the start to the end of the list, and we'll find ourselves in positions where we want to remove particles, notably from the active particle. So whenever a particle comes in the lifespan, we want to take it out of that structure and push it back onto free particles. So that being the case, a linked list is the appropriate data structure to use. Down here we have the particular particle settings that we're using for this particle effect. That's all our values. In terms of the constructor here, so we pass in the context to which the particle effect is going to, emitter is going to belong, and we pass in the initial set of settings that we're using. What we do there is we create our new active and free particle lists. To get things going, we create a bunch of 100, in this case, starting particles. None of these are live at the minute. These automatically get pushed onto our free particles, but they give us a bunch of particles that we can use to help drive any particle effects whenever they come along. Then call configure. Now, the reason we call configure, you'll see actually from this method down here, is that other than constructing the particle emitter to use a particle settings, we can also come along later on and say, I want to change the particle settings that this emitter is using. And we do that when we change from one demo to the next. So if we're changing the particle settings, we're basically restoring it. In this case, we are going through all of our active particles and we are removing the active particle. And as a reminder here, we're using an iterator as a safe way of being able to iterate over a collection and to change that collection at the same time. So in this sense, we're iterating over all of our active particles and we are actually removing them from the linked list. Not getting rid of them, we're adding them into our free particle list. So that if we did change our particle settings mid-effect, then we would remove all of the existing ones we have, store them, and we'll kick off a new particle effect. And again, we call configure here. So configure is called any time we define or say we want this emitter to use this particular set of properties. So when we call that, the first thing we do is we try to load in the bitmap associated with that effect. So this assumes that an effect has one bitmap. It's a common assumption. You could have more fancy effects where you have a small pool of bitmaps available that are sort of similar to one another. So again, you could extend this if you wanted to. We store the texture center and we set up the type of paint that we are using. So this depends whether or not that particle effect uses normal alpha blending or additive blending. If it's additive blending, then we set up the paint to basically the paint mode to be add. Now we've got a couple of private vectors here for particle position, particle offset. We define these here as private variables because we'll be using these frequently. A vector2 is a class, so we don't want to be calling methods frequently where we have to create vector2s. That would be involving object creation, which would then ultimately have to be putting a load in the garbage collector. So particle position, particle offset, we will use these often. We create them up front to minimize the amount of objects we're creating overall. We've got a method then for add particles. And this gets to be called within our particle world class anytime we want to add in a new set of particles to it. That it's time, for example, for a new burst, for a new explosion, or we've moved the mouse and we want to say here's a new location. So we're adding in particles, we specify the location at which we want to add the particles in, and we also specify the last location if we are using a particle effect that wants to display things contiguously over space. So for some of the effects, for example, the explosion, all of the particles will be created at the location and we'll ignore the last location. For the other one where we were moving the mouse and we had a nice stream appearing behind it, we'll use the current location and the last location to give us that straight line over which we want to create and pin our particles. Having done that then, first thing is we decide how many particles we're going to create. And this is where all of the randomization comes into this. So we are creating a random number between min and max number of particles. That sets it up. We're checking here to see what type of mode we're in. Is it going to be a burst mode or is it going to be continuous? If it is burst mode, then we're assuming here that we're creating them just at the current mouse location. We don't need to worry about any offset for that. If it is continuous, so that was the case where we had a strung over distance, we assume then that we're interested in the last location and the current location, and we want to have an offset that will set them out over that particular chunk of space. And the offset we set here is something that will enable us to step through each particle as it is created and to uniformly go from the last location all the way up to the current location. Having done that, we then actually configure each of our particles that we have within this. So it's from 0 to num particles, whatever random number that was. We want to then have a particle that we're going to initialize, and we check to see our free particles. This is our list of available particles that we can recycle. Now, if it's empty, it means that we're using all of our free particles. Now, we don't want to stop things, but in this case, we say, let's actually create a new particle. So we're getting an additional one. And when we finish with that, we'll push that back into our queue. So we'll not be deleting things. If else is true, it means that we do have available particles. In this sense, we just simply remove the last one that's in our list of free particles. And that's the one we're going to reuse. Now, down here, we have our particle P available, and we want to initialize that. So this is going to be giving its random speed, its random orientation, but we also say here's the location at which you should be created. And the location is the thing that will be dependent upon the burst mode. Either it will be at the current location, or it will be calculated to track between the previous and the current location. So we pass that in. Having then initialized that particle, we add it into our list of active particles. It's now part of the simulation. The bit down here, we're adding in the particle offset. That will only have any significance if we are doing a continuous particle effect where we want to step over time from the last to the current location. That sets it up. Down here, we're going to initialize a particle individually as opposed to the whole set. And again, for reasons as we mentioned, we want to calculate a direction of a velocity and acceleration. We don't want to, within this particular method here, to define these because vector2 is a class, which means every single time we initialize a particle, we don't want to create 3 additional classes, which we then have to remove at the end. So we're creating these things up here. We can reuse them within this class. Inside initialize particle, we say here's the particle we want to initialize. Here's the position at which that particle will exist. From doing the things then, we're picking a random direction based on the min and max orientation. We're picking a random speed between the min and max speed. And this basically is going to be the case all the way down through this here. So we're setting the velocity. We're randomly picking a lifespan between the defined min and max. Same with orientation, same with angular velocity, same with scale, same with scale growth. A little bit down here where we check to see what type of acceleration mode that we have. So there was 2. One was aligned, the other one was non-aligned. If it is aligned, it means that the acceleration is in alignment with the direction of movement. It is along the direction of movement. Or if you give it a negative value, as it was in the explosion, it's going to be in the opposite direction of movement. So this can determine if the random direction that we gave the things, if we're also going to pick our acceleration to be in that same direction. If it is non-aligned, it basically means that whatever velocity we might have given it, that's fine. The acceleration can be in a completely different direction. So again, we can set things up here as need be. Having randomly selected then all of these different values, including the direction, the velocity, the acceleration, and a few of the scalars, we can finally go to the particle and say, here's your bunch of initializing values. They'll be accepted in, they'll be stored. Update and draw. So this is update and draw of our particle emitter. If we're updating it, we're passing in the elapsed time and our current location, for example, for the mouse, because we needed this when we're doing the continuous movement. We have a small check here to see do we need to trigger any more particles. We're checking there our time to burst figure, and if we do have time to burst being triggered, then we'll randomly we'll select then our burst and a value between our min and our max burst time. So again, we can randomly change how often we're creating these things. We'll add particles in. Location, last location, and we're storing our last location. So next time we come around, we'll know whereabouts it is we were. Having done that, we then want to go through and to update each of our active particles. So the first bit basically says, do we need to add in any new ones? The second bit says, let's update all of the ones that are currently active. So we're creating an iterator, and we want to create an iterator because when we're stepping through our active particles, we'll probably find some that have exceeded their lifespan, and we then need to remove them from that particular collection. So we've got our iterator, stepping over that. Whilst we have more things to iterate over, we get our particle out. We go to the particle and we add on whatever gravitational acceleration has been set to this. So we're adding that onto the velocity. Gravity is updating the velocity. If gravity is set to 0, no change will be made to the velocity. Having done that, then we then go to the particle and we ask it to update itself. And as a reminder, when we were updating the particle, What we're basically updating is the velocity, the position, the orientation, the scale, and updating the time since birth. So simply updating those factors. Having done that, we then come back. Now, part of this update, we'll have updated the time since birth. We can check then to see, is that particle still alive or has it exceeded its lifespan? If it has exceeded its lifespan, we remove it from our list of active particles and we add it into our free particles collection. So again, just the types of things you would expect to have happened. And that's really all of the update. So every once in a while, we'll create a bunch of new ones, randomly selected within defined ranges. Normally, we'll simply go to each particle, ask it to update itself. Whenever itself has come to the end of the lifespan, we remove it and we recycle the object. For drawing it out, we're going to be using a matrix to draw these things out. And again, a matrix is a class. We don't want to be recreating it every single time we draw it. So we store an instance that we'll reuse when we're drawing this out. So for the draw, in this case, we're drawn to a canvas and we're given in the actual game time. Don't really need to use that one here. Each particle in active particles, these are the things that are visible, that we'll be drawing out. Now, there's a bit of an assumption here, but it is an assumption, and if I'm brutally honest, I think probably would be better to embed this within the update as opposed to make an assumption within our draw method. It's quite common within particle systems that you don't want things suddenly to pop into existence or to pop out of existence. Instead, you want them to fade in and to fade out. It's less visually abrupt. So what we have within this here is a little fragment of code that will change the alpha value of our paint. And we set it up so that we fade them in, the particles in at the start of their lifespan. As they're approaching the middle of the lifespan, it's getting brighter and brighter. At the middle of the lifespan, they'll be fully visible. And as they approach the end of their lifespan, they'll fade out. So you'll see them, well, generally because you have a lot of them together, they fade in and then fade out. And that helps by way of not having things pop in or pop out, which would be noticeable to the player. So this is fairly common. It assumes a particular speed of fade in and speed out here. That's the bit that's a little bit arbitrary, and ideally that's the time that you would want to tie into the particle settings so you can control for that effect just how quickly things fade in, over what section of their lifespan they're fully visible, and how quickly they fade out to be not being visible at the end of the lifespan. So that's an improvement then you can make to the code that we have there. Beyond that then, we're simply setting up our matrix. So we set it, the normal things hold, start off with an identity matrix. If you want to scale, you do so. If you want to orbit, you would do so, or rotate around the origin. There is no orbit in this case, and then translate at the end. That sets up our matrix correctly, so we're able to draw the points correctly. And we go to our canvas, we're drawing out the bitmap associated with this effect, using the matrix that we've calculated, using the paint that we've calculated. So the paint in this case will contain the alpha and will also contain whether or not it is additive or normal alpha blending. That's really all that we have to it. So it's not really a huge amount to this in terms of how it works, but it's a very flexible structure and is the type of thing that you can add on lots of different fancy bits to. You can create different effects, you can enrich and make the effects that we have here a good bit more complicated. So certainly consider if it is of relevance to the game that you're developing. If it is, feel free to make use of this, to adapt it, to extend it as you see fit.